Hello and welcome to day 5. So today we're going to talk about a shift in the way science was seen in the early 19th century. And as a result, it changed the way that modern science is both categorized and practiced. Now, at the end of the 18th century, natural history, which is fundamentally the study of things that exist on Earth, as opposed to things that exist in the heavens, or which are mathematical or general sciences like physics. So natural history to this point had been very largely collecting facts and organizing them. There was some theories out there, but they were not well established. And the 19th century is when most of the theoretical ideas about the living world were developed. So it's an interesting period, but it's also interesting because it changes the way people conceive of things. For example, when Linnaeus did his three kingdoms, animal, vegetable, and mineral, there were still people who believed that minerals grew in the earth and were therefore of a similar kind to animals and vegetables, in other words, plants. So there were three sub-disciplines at this stage: zoology, botany, and mineralogy. There are a number of other disciplines that were either social or the intersection of social and the natural world. For example, geography was a very interesting one. Geology developed out of mineralogy, and biology itself, well, it's a term which initially meant physiology, or rather the functional ways in which natural living things behaved. In 1799, Thomas Beddoes, in his essay in Contributions to Physical and Medical Knowledge, he wrote, and I quote, "Physiology, therefore, or more strictly biology, by which I mean the doctrine of the living system in all its states." Shortly after the turn of the century, in 1802, Gottfried Reinhold Treviranus and Jean-Baptiste Lamarck both used the word biology, either in French or in German, but it is generally thought that Treviranus's six-volume Biologie oder Philosophie der lebenden Natur, which is another way of saying biology or the philosophy of living nature, had introduced the word biology into German. And from these two sources, English started to use it as a statement about a science rather than just an approach. Now, reportedly, Linnaeus had used the Latin term biology in 1736, which was translated as biologia in 1771 translation, a German translation. So the word had been around for quite a while, but it wasn't seen as the name of a science until that point. Likewise, geology. It developed, as I said, out of mineralogy, which was of particular interest to both collectors but also miners. So obviously mining is an economically significant activity. And mostly what they were looking for were metals, but also crystals, such as various crystals of carbon, of silicates, and so forth. They didn't at the time know that that was what they were crystals of. So the German Renaissance physician in the 16th century, Georgius Agricola wrote works such as De Re Metallica on the metals, or on metallic things in 1556. And after that, before that, he had written De Natura Fossilium. Fossil is a Latin word that means stone or rock. So when we talk about fossils or fossilized organisms, we're talking about organisms that are or have been turned to rock. Okay, there's a whole backstory to all of that, but I'm not going to go into it. Now, systematic scientific studies of minerals and rocks developed after the Renaissance, and the modern study of mineralogy was founded on the principles of crystallography and the ability to study rock sections with the invention of the microscope in the 17th century. Agricola's text was basically the handbook for miners for about 2 centuries after that. It was one of the reasons why mining academies and schools of mines and the like started in the 18th century. So that by the 19th century, these were significant educational institutions, and geology by that time had become a recognized and significantly important science, economically important. So if you've got a science, you've got taxonomy, haven't you? And of course, we had animal, vegetable, or mineral in Linnaeus's Systema Naturae. On the left, you will see an image that was published in 1770. The first edition of Systema Naturae had no images, but over the years, as he became more wealthy, he was able to put these in. And you can see that Linnaeus classified by shape, and only by shape. He actually held the view that no other properties of minerals were of interest because you couldn't organize them into a systematic classification, whereas with this you can. This also is about the period where people start to make what are called orographic maps of minerals. And on the right-hand side there, you'll see one from Berlin Natural History Museum, which shows the position of, the locations where certain minerals are to be found. Orographic mapping, by the way, is called topographical mapping, or GIS, and so forth. But at the time, it was simply a way to represent hills and valleys on maps. So this is an early period before we come up with the idea of height mapping with lines and so forth. Okay. So today we classify minerals in terms of their shape, yes, but mainly in terms of their chemistry, whether it's a silicate or a sulfate or carbonate, something like that, and its hardness, based on a scale that was introduced in the 1820s in Germany under, I think it was Karl Mohs. Called the Mohs hardness scale. Now, shape is still important in those minerals which form crystals, but not all do. All right. So, last lecture we talked about voyages of discovery, and while there were traditionally people doing some sort of science, usually navigation, surveying and cartography, but also astronomy, in these voyages, that was not why the voyages were run. In other words, the scientific activities were a consequence of exploration and not the cause of them. Many of the people who undertook the voyages, their captains and so forth, they had a good education, and to be a navigator, you needed to understand astronomy, mathematics, and to a degree surveying. But this was done incidentally to the main task of the voyage. Beginning in the late 18th century, we start to get scientific explorations. These are explorations which are undertaken.
I didn't get that. Could you try again?
Excuse me. Those are expeditions which are undertaken in order to find out something scientific. I'm just going to turn my phone off. Okay. One example of this is by someone we've previously encountered, Pierre de Maupertuis, a physicist who was sent by the French government to the equator and to Lapland in Norway and Sweden, because at the time Sweden held both areas. And another one was sent, another expedition was sent to the equator. And by measuring the arc of approximately a degree's length, they were able to show that the southern end of the arc and the northern end was flatter than it was at the equator. And this was Newton's prediction that the Earth is slightly flattened. There's a good book, which I've got in the shelf somewhere, but I can't find it right now, called The Man Who Flattened the Earth, if you want to know more about Pierre Maupertuis. Now, another book I've got is on transits of Venus, and what was going on here was they were trying to get a relative estimation of the distance to Venus and the Sun by measuring how long it took for Venus to transit the Sun. Transits of the Sun were rare, and what they tried in 1761 and 1769 was to send expeditions all over the Earth, and only two, I think one in Africa and one in the Pacific, were able to get measurements, and the one in the Pacific was not reliably done. Their technique was bad. So it's an interesting story and a good book to read if you're interested in that sort of stuff. I'll find the information and put it up on the website. Now, of course, there were particularly 3 voyages between 1768 and 1779 from Britain. And this was a bit of competition between the Royal Society and the Royal Navy, and in the end, these official voyages were required to include at least an astronomer and a botanist. But since these voyages were substantial and were going to places that Britain didn't know a lot about, they sponsored private naturalists, particularly Joseph Banks. I've already mentioned one of them, which was Andreas Solander, a Swedish student of Linnaeus's. And so these expeditions were partly scientific and partly military, political and economic. All right, so that's the 18th century. Something changes in the 19th. We get a movement that these days is called Romanticism in English. And in science, we refer to them by their German name, the Naturphilosophen, the nature philosophers. Unlike the fairly workaday English style, and to a degree French style, of science in the 18th century, which was heavily mathematized and very procedural, methodological, the Romantics held that something is left out of science when you do it that way. And so they emphasized emotion and individualization. They glorified all of the past and all of nature, preferring the medieval rather than the classical. Now, this is partly a reaction to the Industrial Revolution, but also to the aristocratic social and political norms of the Enlightenment. Remember, the Enlightenment was not a popular movement. It was something that only those who were well enough off to spend time reading a lot and buying books were really able to access. The scientific rationalization of nature was something they did not like. In other words, all components of what we now call modernity. And in particular, the dark satanic mills, as a poet referred to the Industrial Revolution, which was in high flight at this time. This is something that also applied in the visual arts, in music and in literature. And you can see Mary Shelley there, who wrote Frankenstein, which is a classic romantic or Naturphilosophen book. It's a critique of that version of science that the Enlightenment proposed. But it also had a major impact on the way history was done. We saw the invention of great man theory by romantics in Germany, in England, where history was the sequence of the activities of individuals rather than anything more general. And it also influenced education, the social sciences, and of course the natural sciences. Mostly, however, it had a very significant and complex effect on politics. For example, they influenced liberals, that is, people who believe government should not intervene in private lives, radicals who believed that governments needed to provide for people and not just let them die, and conservatism and nationalism even. So they influenced all of the modern political views. All right, so what was it that they proposed? Well, they emphasized intense emotion, something like aesthetic appreciation, apprehension, horror, terror, and awe, aesthetic categories of sublime nature and beauty in nature, elevated folk art and ancient custom to something noble, but also spontaneity as a desirable characteristic, as in the musical impromptu. We would call it improvisation in these days. So in contrast to the rationalism of the Enlightenment and the classicism of the Renaissance, Romanticism revived the medievalist approach of an artistic view of nature. Also at the time, we're starting to get explorations of nature in place, in situ. There's a picture of a very famous French botanist, Bernard de Jussieu, going out and botanizing, as it was called. He was well known for classifying enormous numbers of plants. Moreover, we have scientific laboratories other than chemistry in order to do experimental inquiry. So what we see is, at the same time as the Romantic movement, we see a more exact type of science developing, which of course means precision and measurement. And this meant that you had to increase and standardize the number of instruments that you used. It couldn't just be a description anymore or a drawing. You had to measure things. Now, initially, this is what the physicists did, Coulomb's torsion balance here to measure electrical attraction and repulsion. And once you have got something like that that can be remade elsewhere, you can you can develop standardization. So big data has its beginnings here. This is also about the time we see the emergence of meteorology. Previously, there had been folk rules, you know, red sky at night is shepherd's delight, red sky in morning is shepherd's warning, and all that sort of stuff, which works in the northern hemisphere but not in the south. But what we've got developing here is measurements of temperature and air pressure at a number of places. This is an observation chart from the St. Gotthard mountain in Switzerland for December 1781. Over time, we start to get an organized observation network, which of course raises the issue, are we all measuring the same things in the same ways? So a couple of geologists, Jean-André Deluc and Horace Benedict de Saussure, did their science while mountaineering. Previously, mountains had been somewhere to avoid, to go around, right? You didn't go up a mountain. It was not seen as anything important. But these two guys were, Saussure was born in what's now Switzerland, in Geneva, and there are a few mountains around there. So in order to do science while they were up mountains, measuring pressure, temperature, moisture, and so forth, they had to develop things like portable barometers, hygrometers, thermometers. They both developed a hygrometer, which measures moisture in the air, and they were different. One was based on whalebone, and the other one was based on hair, and of course they ended up having a scientific controversy, as scientists are wont to do. Deluc is the guy who suggests using mercury in thermometers. He gave the first correct rules for measuring heights with the help of a barometer. He sent a long paper to the Royal Society in 1809 separating the chemical from the electrical effect of the dry pile, which is a type of voltaic pile that generated electricity, and so on and so forth. Now, Saussure carried barometers and boiling point thermometers to the very summit of the highest mountains. He adapted it for many purposes. He would use one with a fine bulb hung in the shade or whirled by a string, the latter being converted to an evaporometer by inserting its bulb into a piece of wet sponge. Wake up. A piece of wet sponge and making it revolve in a circle of known radius, etc. He also was able to measure the temperature at the depth at the bottom of deep lakes, and was able to show that deep lakes are uniformly cold at all seasons, and that seasonal changes in temperature take 6 months to penetrate to a depth of 10 meters in the earth. So they noticed changes in the atmosphere as they were climbing heights. They weren't the only people who did this. On the left there, you'll see that a French fellow by the name of Florent Perrier measured the atmosphere for Blaise Pascal, the French philosopher and mathematician and theologian. Saussure wanted to also measure the blueness of the sky and invented a thing called the diaphanometer for judging the clarity of the atmosphere, the anemometer, and something called a mountain eudiometer. Okay. On the right, you will see one of the peaks that he went up. In fact, you'll see him going up that peak, because he's a very tiny little figure there with his assistant, up a mountain called Don du Jean. Here it is, slightly bigger. Okay, and this is from his own book. Travels in the Alps, preceded by an essay on the natural history of the surroundings of Geneva. So we're starting to see people doing exploration science and developing new instruments. There's the hygrometer using the whalebone and the barometer of Deluc. And because we've got precision, we can compare measurements made by distinct and different instruments, and we can standardize over that. Dassault invented a simple gauge. This is a cyanometer, which is basically a wheel painted in different shades of blue, given numbers. It didn't really provide very much useful information. The scientific community abandoned it not long after. But he did record that the sky at the top of Mont Blanc was almost black. And in 1802, the next guy we're going to talk about, the German explorer and scientist Alexander von Humboldt, who I've mentioned a few times, he got to the 46th degree out of 50 on top of the Andean mountain Chimborazo. It's actually a volcano. All right, so if you're going to go on a trip to the Amazonian rainforest, to the Chilean Andean peaks, to Mexico, etc., and so forth, and you want to do your work while at the same time being a romantic scientist, that is, looking at things as a living whole, then you're going to need a portable laboratory. Here's a painting of Humboldt with I'm not sure how you pronounce that, Bonpland in the Amazon rainforest. It's a painting some years after, but it gives you an indication of the sorts of instruments and packaging that they would carry. They wouldn't carry them, by the way. Their guides and locals would carry them on their behalf, but let's not let that act of colonialism distract us. So here's a list. I'm not going to go through it now. You can have a look at this in your own time, of what it was that they took with them. 2 barometers, 2 hygrometers, 2 electrometers, an eudiometer, there we go, to measure nitrous gases. They were doing something very akin to what we would think of as modern science. Now, Humboldt's view of science was incredibly influential because he wrote a book about his travels, and it was read by everybody. Anyone who had an interest in the natural world read this book. And consequently, he influenced the nature of European science extensively. You had to be precise in your measurement. You had to disregard previous theories because they were verbal, they weren't mathematical. You had to use mathematical tools to analyze your data, and you had to search for measurements at every possible place. Okay? He saw a need for an approach to science that could account for the harmony of nature among the diversity of the physical world. For him, the unity of nature meant it was the interrelation of all the physical sciences, including biology, meteorology, geology, physics, chemistry, etc., that determined where specific plants grew. He found these relationships by lots of painstakingly collected data and that data was extensive enough that it became an enduring foundation on which others could base their work. He viewed nature holistically. Now that's HOLISTICALLY, not WH. Now, holism is the view that the whole, WHOL, is important to understand the parts. Sometimes holism is the view that the whole is more than just the sum of its parts. The alternative to that view is called reductionism, and it's the idea that you can take a whole and reduce what it does as a whole thing down to the activities of its parts. So the whole is just the sum of its parts. He believed in the central importance of observation and had a massive array of the most sophisticated scientific instruments then available. Nothing quantifiable escaped measurement. Okay. He wasn't the only person doing this at the time. In 1815, which is not long after Humboldt's training, the British English geologist William Smith, referred to as William Strata Smith, he did a geological map of Britain, mostly of England, showing where all the different types of rocks were, and this became the first such map. Humboldt was trained in mineralogy, and he knew about stratification as a geological process and a geographical process, the way that Smith had done it. In the geography of plants, he took mineralogical thinking over into botany. In part, he based this, as many other people did, on Johann Gottfried Herder's Ideas on the History of Mankind in Philosophical Perspective, which is a source text for a lot of romantic thought. And in that book, but not uniquely in that book, Herder says that humans adapt to their climate, and culture is the result of that adaptation, and that human variability is caused by different climates. Anyway. So, stratification, plant geography, and human variability. Humboldt's travels were not as long as you might expect. He travelled to, what are they called? The Canary Islands, and did work there. Another person shortly afterwards, Leopold von Buch, did a complete workup of the flora and fauna of the Canary Islands that was influential on Darwin in the 1840s. Then he travelled to what is now Guyana, but at the time was a Spanish single region, New Granada, and he travelled through that region, and part of it was into the Amazon, not further down where Wallace went later on. Then he travelled through the Caribbean, spending time in Cuba, then back to New Granada, down the west coast to Chimborazo, and from there he went to Mexico, from Mexico back to Cuba, and then to the United States. So it was a good trip, and it took him 5 years, but it wasn't what you might think of as a global trip. So in the course of doing this, he would make paintings of the area as scientific diagrams. He called them Naturgemälde, nature paintings. So this is one for the Chimborazo volcano, and he details it in cross-section with information about where the plants are found and the elevations that they're found at. And it was published in his book, The Geography of Plants, in 1807, in a large, obviously hand-coloured format. This is the mountain in question, okay? And it is also taken from one of Humboldt's and Bonpland's paintings, and was the subject of later romantic nature paintings like this one, painted in 1810, showing Alexander von Humboldt and Imre Bonpland at the foot of Chimborazo. And here you see Humboldt showing his sextant to an Indian guide. No, that is not a code word for anything. While Bonpland works on specimens under the canopy, and you'll see a barometer hanging on the tree next to Bonpland. Navigating in the sea, this sort of sextant was one of the navigation tools invented in the 18th century by British mathematical instrument makers, and it permitted mariners to find their position much better than before, although really it only gave you the latitude, not the longitude. Jesse Ramsden, who made this sextant, also devised a machine that would engrave the scale on the sextant very exactly. So again, precision. So with all this data, Humboldt tried to figure out a way to relate it, and he wanted to relate it in a visual format. Now, the thing that he came up with was the showing of lines between places which had the same value. They're called isolines. An isobath is a contour line of constant depth in the sea, and that's earliest found in 1584 of the River Span near Haarlem. Edmund Halley used isogons as on a chart of magnetic variation. Dutch engineer Nicholas Cruquius drew the bed of the river Merwede with lines of equal depth, isobaths, and so on and so forth. You find them more and more. When the Ordnance Survey in Britain around 1843 started to record contour lines in Great Britain and Ireland, they were already in general use in European countries. Now, doing this gave people a way to look at the whole and see the shape of the whole, right? To look at the whole thing. Why is it that temperatures vary in this way? Why is it the pressure varies in this way? Why is it the depth varies in this way? So it is a way in which to approach the world as a unity. We do these sorts of things now. You guys probably haven't been taught how to read a meteorological map of isotherms and isobars and what have you. I was, because they used to publish these every day in the newspaper, and from looking at them you could tell which way the wind was going to go, what the rain was, was there going to be rain, was it going to be cloudy. There's a lot of information packed into these things. These days, not used quite so much. All right. So, arguably, Humboldt invents the modern idea of nature. And he published a book called Cosmos in 1845, 1847. The second volume in 1847 is now available in English. Again, it's on the shelf somewhere. And it was very influential to the reading public. It posited that nature was one thing and that there was a universal life force perceived only as a whole. You couldn't just look at bits and pieces like they did in museums. You had to look at the whole thing. He relied quite heavily and explicitly on his local indigenous guides, and didn't hesitate to give them a mention. But mostly he was interested on the appearance of the plants. How does the fauna look as a whole thing? We would today say, what's the ecotype? What's the ecosystem like? What's the biome? And we owe this in some degree to Humboldt. Moreover, Humboldt introduced what we now call biogeography, which is mapping types of habitats around the world. And he strongly influenced Alfred Russel Wallace, he of the one L in the middle name, who came up with a way of classifying what he called biogeographical regions. And this is something that Humboldt gave us. But I would like to say one thing about this book. It's a good book. It's got a title I do not like. The Lost Hero? Really? Everybody knows about Humboldt if they've studied any of these fields in their history. He's not lost. Wolf does a good job of sort of bringing all of his stuff together, but she's not the first to do that. And there's been books on Humboldt since Humboldt wrote his books. I think it's a bit of an exaggeration. Always avoid speaking of heroes or forgotten people or lost figures in history. It's generally not true. All right, we finished a little bit early for the first lecture, which I'm sure is a great comfort to you all after yesterday. We'll have our usual break and start back here at 5 past the hour. And our next lecture will be on deep time and neo-catastrophism. And it's a fun one. Okay, thank you. So, this lecture is about deep time and catastrophism, which are two of the ideas that have developed in the context of modern geology. I introduced geology in the last lecture. At this point, we're talking now about geology in the very late 18th and early 19th centuries. At that time, there were fundamentally two different views. One was called catastrophism and the other was called uniformitarianism. Now, catastrophism was introduced to deal with what seemed to be changes in the geological record, particularly with fossils, where you would find different ranges and different types of organisms, particularly animals, in different geological eras. Baron Cuvier, Georges Cuvier, who was the founder of vertebrate paleontology in the 19th century, very early in the 19th century, had done his initial work on the Paris Basin, in which he looked at fossils of fishes. Now, the Paris Basin was a sedimentary basin, so he was able to show that there were different geological eras and each one had different animals. And so he proposed, without there being a mechanism in his work, he proposed that there were different catastrophic cataclysms or revolutions. He wrote a book called Revolutions of the Globe, which explained different animals. And so each era had new creations. Also, he allowed that there was a lot more than merely biblical scales of time back into the past, but he didn't do much in the way of estimating that. But around about the time he did this, Buffon had also started doing some experimentation to see how long it would take the Earth to cool. And from memory, I believe he came up with something like 100,000 years. So this is a major advance over the biblical scale that people had been thinking in. In the late 18th century, a fellow, the Reverend Hutton, studied a region called Hutton's Unconformity in Scotland. And you can see a photograph of it at the bottom there. Now, it's not entirely clear from the photograph, but the diagram that's given at the top shows how you've got horizontal sedimentary layers, and then suddenly you've got sedimentary layers which are not only at right angles, but they're also compressed and deformed, and that you've also got a layer of scree, I guess you'd call it. So at some point, Hutton reasoned, given that the sedimentary layers are formed by deposition in water and are probably seabeds, the seabeds have been rotated. And this meant for him and those who followed him, in particular Charles Lyell in the 19th century, this showed that the history of the Earth was even longer than Buffon had suggested, and we're starting to see terms like millions of years. The age of the Earth becomes a major topic of investigation and discussion throughout the 19th century, and actually the age of the Earth as we now have it wasn't resolved until the discovery of and measurement of radioactive decay in zircons, which showed that the Earth was something on the order of 10 billion years old. I think we now have it at 13.87, something like that, I can't remember. You can look it up. All right, so volcanism also added to the surface of the Earth. Erosion took mountains and eroded them to form these sedimentary layers. And in Huttonian geology, there was no catastrophe, no sudden revolutions at the beginning of the 19th century, because that was seen as either a quasi-religious explanation, which had no place in science, or it was seen as something almost superstitious. So the principles of uniformitarianism, we were already on that. Principles of uniformitarianism were that the forces acting now are the forces that were acting in the past, that they act gradually and without sudden changes. So the uniformitarian view, which was named in the 1830s by William Whewell, who we will return to, basically had what you might think of as mundane, everyday causes generating the landscape. Now, what's interesting about that is that the everyday causes are the ones that we can observe. We can experiment with everyday causes. We can test how long erosion takes. We can see how long it takes to deposit a layer of silt in water, and so on and so forth. So it became much more tractable as a science, whereas the catastrophic view relied upon rare events, and they were very hard to study and had not generally happened in our lifetime. The mechanisms, therefore, became known as volcanism versus Neptunism. Very bad classical names for that period. So there was a theological issue at play. If you were a Neptunist, then you could say most rocks are the sedimentation of primordial waters, which had been an explanation for rocks by Thomas Burnett's theory of the Earth back in 1697. And if you know your biblical story, then you know that all the mountains were covered, which means that these waters, the waters of the flood, the deluge, caused most of the sedimentary rocks that we see today. Volcanism, or Plutonism, held that rocks are formed out of lava, basically the result of fire acting on matter. And the age of the Earth was something they also differed with. So here's an illustration showing the Paris Basin from Cuvier and his colleague Brongniart's study, and you will see that you have quite easily relatively datable. They didn't know the absolute age, but they knew which ones were earlier and which ones were later because it was just basically there in the record. And consequently, the Neptunists held that this showed epochs, all right, but they were epochs over thousands of years rather than a few years, whereas Cuvier thought that each strata boundary was explained by a sudden change in the conditions. Now, what's worth noticing here is that sudden is one of those terms that's entirely relative. These days, if you're a geologist and you say there was a sudden change at this boundary, you could mean something that happened in a couple of weeks, like the KPG, Cretaceous Paleogene boundary, which was caused by the asteroid that hit us 66 million years ago. Or you could mean it sudden as in it happened in a period of only 1,000 years. Sudden is a very relative term in geology. And when people start talking about these things, you get ambiguities that debates trade on. So at the beginning of the 19th century, catastrophism had everything happening more or less at the same rate daily. And catastrophism, everything happening in some unspecified sudden timing. By the end of the 19th century, basically the only difference between the two views was in the words that were used. Uniformitarians allowed earthquakes and what have you to cause uplift. Charles Lyell's book even showed an etching of this. And for seas to rise and fall, and catastrophists allowed that there would be change between these revolutions. So to give you a look, the catastrophists included James Hutton, as I mentioned, Georges Cuvier, and these people, this view, although it fell gradually out of favour, is still around us. People argued against the idea of the asteroid causing the extinction of the dinosaurs and the KPG layer because everybody was supposed to be a uniformitarian. But that's a debate that is more or less resolved these days. But for our purposes, what's interesting about this is that Charles Lyell enthusiastically became a uniformitarian in the 1820s and 30s, and when Charles Darwin travelled on his voyage, he was handed, I think, the first volume of Lyell's newly published Principles of Geology, in which he presented a uniformitarian view, by his tutor at Cambridge, who said, on no account believe any of this, but you must read it. Now, ironically, by the end of the voyage, Darwin was a convinced uniformitarian. And that influenced not only his view of nature, but his view of the lands on which nature evolved. Okay, so the idea that the Earth is old isn't particularly new. The Europeans knew, for example, that Hindu teachings held that the Earth was almost infinitely old, at least in human terms. And Benoit de Maillet, who was a French diplomat, used the clever cipher of reversing his name to write a book called Teleomed. I'm sure many people were fooled by that one. And he used the device of a Hindu wise man telling a missionary that the Earth was 2 billion years old. It arose in the sea, and humans arose from marine life forms. Now, this in no way really represents Hindu teachings, but de Maillet was introducing the notion that the Earth was very old and that things had happened over very long periods in the deep past. This is a different view of the way the world exists. It changed our mind. So Hutton and Lyell and Darwin all argued that the world was unimaginably old. Now, for Darwin, that was hundreds of millions of years. He didn't have a reason to think the Earth was much more than that, and he got a bit of stick from William Thomson, later Lord Kelvin, because Kelvin said that the sun could not be more than 10 million years old because it was thought at the time that the sun was heating because of gravitational collapse. They didn't know, for example, about fusion. They didn't know about radioactivity. And Darwin stuck to his guns, but was increasingly under pressure later in his career. And a great many people thought that the physicists had to be right and a biologist couldn't overturn physical principles. The story goes that Ernst Rutherford, the New Zealand physicist who basically discovered and explained radioactivity, that he gave a talk at which Thomson/Kelvin was attended, and he was very worried because he was a young scientist at the time, and he was trying to introduce the idea of radioactivity to people who didn't know about it. And he was very worried that Kelvin was going to have a go at him because he had a famously acerbic tongue. So what he did was he said, Lord Kelvin has wisely noted that in the absence of any other form of energy, the sun could not be longer than 10 million years old. And he was prophetically right. There is another form of energy. And apparently Kelvin harumphed and went to sleep in the talk. Okay, so this is from a book, John McPhee, in his book Basin and Range, which was published in 1981. And in that he said, numbers do not seem to work well with regard to deep time. Any number above a couple of thousand years, 50,000, 50 million, will with nearly equal effect awe the imagination. Consider the Earth's history as the old measure of the English yard, the distance from the king's nose to the tip of his outstretched hand. One stroke of a nail file on his middle finger erases human history. Here's a diagram, which you saw before, showing that at the very least, life is very deep, but that if you notice around about the tip of the first figure, you see the dinosaurs, and they lasted a reasonably long time. So the Phanerozoic eon is the period after animals form. The proteozoa, I can't even say it, is a period in which there were only single-celled organisms or microbial mats, and possibly the beginnings of things like sponges or or jellyfish, maybe. For a long time, the US Geological Survey diagram here was republished in books because it's a government diagram. People can use it again and again without paying for it. And you'll notice that life begins after many of the spirals, and that the human period, which is in the very top, the very end period, which, if I'm not mistaken, is, no, I can't see what it is. Hang on a second. The Holocene, right? Yeah, the Holocene period, which includes not just all of human history, but pretty much everything for about 20 million years or so. And going back to this diagram, the whole of human existence is about the thickness of that grey line at the end. So I think McPhee was actually understating it. Human history is effectively less than a pixel at the very end of that middle finger there. Okay. A number of people have proposed a more cosmic view of evolution in which our biological era is in effect the most recent stage. But this is something that was put out by Eric Chasson, a physicist, I'm guessing about 10, 12 years ago. And a lot of people kept trying to produce a cosmic evolution view, but they always do something that's a bit of a sleight of hand, and I want to show you this just so that you can see it. So the Big Bang at zero, and you then get sometime after that particulate matter. Now that distance is hundreds of millions of years. The distance to the first galaxies is hundreds of millions of years. The distance to Earth's star is billions of years. To Earth itself is hundreds of millions of years. To chemical evolution, which is the beginnings of life, and so on and so forth. And then biology is 14 billion years, 3.86 billion years ago. Now, if all of that's happening at a regular rate, then the cultural end should be almost identical to the future end. But he spread it out here to show that things are going to go in all of human history. If we managed to travel across the stars and survived as long as any other large-bodied mammal species, which is about 2 million years, if that happened, it would still be a nail file's worth of fingernail on the king's hand. So what we get is this, it's sometimes called the pull of the recent, where we try to expand out the most recent era because we're in this era and it's the one that matters most to us. But in objective terms, I seriously doubt that it's all that significant. Okay, catastrophism made a return in some senses back in the 1920s. Now, there was a fellow called J. Harland Bretz. He was a geologist with the US Geological Survey, and he started uncovering evidence of these massive floods in what's called Lake Missoula. Now, if you've seen Ice Age, the movies, then you've seen that lake. And there was a dam at one end of the lake caused by glaciation. As the glaciers retreated, eventually that dam broke, and you had 400 feet, which is about 120, 130 meter high waves that basically swamped across Washington, Oregon to the sea. That's a catastrophic event. Initially, he was not accepted. This event was dated, according to him, between 15 and 13,000 years ago, creating the Badlands. That's how big the wave was, just by the way. So that's the Washington Needle. If you'd been up the top of the needle, you might have survived. So this is how it looks. You can see all the areas starting in Montana, all the lakes, all the waterways and so forth that were fed by this, not once but multiple times. And you can see the scouring of the land, cleaning away all of its topsoils and so forth, and just leaving the bedrock in the photograph below. Some of the things that it did was it formed these massive canyons. It's not responsible for the Grand Canyon, as far as I'm aware, but there are a lot of places where the action of these incredible waves caused quite a bit of erosion, because it would have taken quite some time for that water to drain away. And if this happened several times over 1,000 years or more, then this is how you get these things started. So I couldn't find a photo of Brett's, but here is his publication, which was published in the Division of Mines and Geology for the US, for the Washington state. And by the 1960s, late 1960s, he had pretty well convinced everybody that it had occurred. They're now called the Missoula floods. Okay, so there's some more information, and there's a very good multimedia site which you can learn about these things if you'd like to go to that link. All right, so what this gave us was neo-catastrophism. And in the late 1970s and early 1980s, a father and son team identified layers of sedimentary layers around the world which were higher than the Earth normally is in iridium, a metallic component of known component of meteorites. So they proposed that the Earth had been hit by an asteroid which had caused major and catastrophic changes to not just the flora and the fauna, but even the very existence of ecosystems. We nowadays see this shown everywhere. It used to be called the KT event because it was from the initials, the German initials for the Cretaceous/Tertiary event, but the Tertiary has been renamed. The Cretaceous has not, just as a little note, if you were going to revive dinosaurs and set up a park and you included the Allosaurs and particularly T-Rex, it would be Cretaceous Park, not Jurassic Park. Okay, so on the left at the top you see the sort of fauna before this boundary, and at the right you see the sort of fauna that you get some 5 to 10 million years after this boundary. Birds are the only families of dinosaurs, theropod dinosaurs, that survived. The reason, we're not entirely sure. They may have at that time lain their eggs in burrows which protected them somewhat. We just don't know. Birds had evolved by that time, and there were birds without teeth and with beaks. All right, so who are the two people that discovered this. One was a geologist, Walter Alvarez. His father was a Nobel Prize-winning physicist, Luis Alvarez. He won his Nobel Prize with Frank Asaro and Helen von Michel. So they identified this iridium layer, and it was noticed that very often the bottom of that layer was filled with microtectites. These are small bits of rock which have been heated upon re-entry or entry into the Earth's atmosphere, and they make a particular shape not unlike a space capsule that's returning or something of that kind. Look them up, they're great fun. Unfortunately, it also gave us the third or fourth worst movie of all time, so we'll blissfully move over this. All right. Sometime later, they discovered where they thought the event had happened, and it's at the top of the peninsula there in Mexico, and the site is called the Chicxulub crater, after the place where the crater is. And you'll see any number of representations of this thing hitting. It was a massive blast. The crater was 180 kilometres in diameter and, briefly, 20 kilometres in depth. I say briefly because there was an isostatic rebound immediately after it. Now, it was found using gravity anomaly surveys to identify oil sites in the Gulf of Mexico. And one of the things that they noticed, in addition to the circular structures, is what are called cenotes, which are natural underground stores of fresh water. So in the impact, certain structures were formed which showed up as weaknesses in the limestone, and consequently they collapsed, causing these cenotes. That's what one looks like. Okay, so these are the tektites I was telling you about. And as I say, they are caused by re-entry and friction in the atmosphere. Well, not friction, heating caused by pressure build-up as they come flying in. And you've got particular shapes that develop if they are even roughly circular to begin with, spherical to begin with. You also find what's called shocked quartz. Now, quartz is discovered wherever there's been an impact, either a nuclear test or a crater, such as this one here, which is in Flagstaff, Arizona. There's a much better one at Wolf Creek in West Australia, which is bigger than this. And there was a massive one in South Australia at some point, but the crater has long since been subsumed by erosion. All right, now, not everybody is happy with this catastrophic extinction event, or global extinction event, and in particular, a geologist named Goethe Keller has argued that volcanic activity in India caused the death of dinosaurs by releasing large amounts of sulfides and nitrites into the atmosphere. This went for a very, very long time, thousands and thousands of years. But recent work suggests the impact itself caused or triggered the Deccan traps, so the Deccan eruptions. So recently a Berkeley team argued that the impact itself caused the Earth to ring like a bell, and as the shock waves converged around the other side of the planet, they converged on the Deccan region, and that generated the eruptions. Now, there was probably a magnitude 9 or greater earthquake around the world, would have shaken a lot of things up. The arguments go on. People keep saying that the dinosaurs survived for tens of thousands of years after the impact, and other people say no, you've got the measurements wrong, and it's a very interesting debate altogether. But underlying it are the issues and the ideas and the emotions that the uniformitarian and catastrophist views trigger in geologists. All right, we're getting close to the end now. I just want to talk about mass extinctions. Now, the history of life since it became multicellular, and particularly since it became land-dwelling, is shown with major episodes of extinction. We call them mass extinctions. So we get 50% of all animal families in the Ordovician. It's the first major extinction, including many trilobites go extinct. You get another one in the Devonian extinction, 30% of animal families. Now, I'd just like to make a point. Family is an artificial rank. There's nothing special about families. So using families to measure the amount of extinction, I think, is slightly misleading. My view is that there's probably all scales of mass extinctions, ranging from local and fairly straightforward, through to global and very strong. But for rhetorical purposes, for public relations purposes, people talk about mass extinctions and claim that there's been 5 of them to date, and we are causing the 6th extinction, which was a book published in 2014, and fits rather neatly in with the work on biodiversity that we'll be looking at in a future lecture. All right, so that gives us an end to today's talk. Today's lectures. We've been covering Humboldt's holistic view of the physiognomy of nature, the overall look to nature, the growth of ideas that leads to modern ecology and biogeography. We're looking at the geological debates between uniformitarianism and catastrophism, and all of this results in what we now call the evolution revolution, or at least that's what I'm calling the next lecture. Thank you.